Hi, welcome to Physics Laboratory. In this module, we're going to learn measurement and significant figures. Here's the outline of our practicum. Objectives, theory, tools and equipment, practicum procedures, and data processing. However, in this video, we are only going to cover the first three of them. First outline, objectives. The module contains 4 objectives to be achieved by the end of the practicum. 1. To learn the measurement uncertainty, simple data processing, and various kinds of measurement. 2. To determine the uncertainty in the measurement process. 3. To understand the concise rules of significant figures and the use of them. 4. Be able to operate significant figures at its concise rules. Second outline, theory. Believe it or not, every measurement always has uncertainty, either done by the tools, the humans operating it, or even by some random uncertainties. There are a lot of causes as what I've mentioned before, such as 1. Tools limitation. There is always the lowest scale value, bad calibration, and friction between moving parts that cause uncertainty in every measurement. Second, observer limitation. As human beings, we are all limited, so there will never be a precise measurement done by humans. Third, random uncertainties such as electrical voltage that change every single time. In our modules, we are going to analyze the data using linear regression. Regression analysis studies the relationship between two or more variables of interest. In regression, there are two variables, independent variable and dependent variable, in which independent variable has the ability to affect the dependent variable. The linear regression formula is y equals to a plus bx. Y is the dependent variable, a is the intercept, b is the slope of the line, and a is the independent variable. To find b, you can use the formula as shown in the PowerPoint. Next, we are going to cover significant figures. What is significant figures? Well, they are the digits that contribute to its measurement resolution, accuracy, and precision. The concise rules of the significant figures are 1. All non-zero digits such as 1, 2, 3, 4, 5, 6, 7, 8, and 9 are significant. 2. 0 between non-zero digits are significant. 3. Leading zeros are never significant. 4. In a number with a decimal point, trailing zeros, those to the right of the last non-zero digit, are important. 5. In a number without a decimal point, trailing zeros may or may not be significant. Here are the examples of the application of significant figures. First example, the number 48,923 contains 5 significant figures based from the first rule. All non-zero digits are significant. Second example, 900.06 also contains 5 significant figures because from the second rule we see that 0 between non-zero digits are significant, so these 3 zeros between 9 and 6 are counted as significant. Third example, 0.0004 only contains 1 significant figure. As from the third rule, leading zeros are never significant, so all of the zeros here are not significant. The fourth and fifth examples are based from the fifth rule. In a number without a decimal point, trailing zeros may or may not be significant. Well, They may be significant if the last number is underlined. As you can see from the last example, the last 0 is underlined, so all of the numbers are significant. You can compare it with the fourth example that has no number underlined, so the only significant number in the fourth example is only 3. Third outline, tools and equipment. In this practicum, we are going to need 5 tools and equipment. The first one is caliper, as shown in the first picture. Second, marker. 3, 500 rupiah coin. 4, pulley. 5, Oahu cent-o-gram balance in the second picture. That's the end of our video. Thank you for watching. I do hope you get some insight about our practicum. I'll see you in the practicum day. Have a nice day.
In this side that we can see on the screen, we're going to measure 3 different values of an object, which are the inner diameter, the outside diameter, and the depth by using calipers as a tool. Okay, the first object we're going to measure is a beaker glass. Let's measure the inner diameter first. As we can see on the screen, you all have to put the tip of the calipers to the beaker glass, and then put the other side of the tip. Make sure you all put the tips properly. Okay, then after that, lock them with this bolt so you all can freely measure the value of the object. Next, the way we measure the object is we have to look at the lowest scale and the highest scale first. As we can see on the screen, the lowest scale of the object is 4 and the highest is 5. Next, we look at where is the vernier or non-new scale started from. As we can see here on the screen, that the 0 of the non-new scale started from 4.1, right here. So you all have to write down the main scale of the inner diameter is 4.1 centimeter right here. Then after that, we look at the non-new scale again and find out where the non-new scale line parallel to the main scale line. As we can see here, the most parallel line between the main and the non-new scale is on the number 2, right? After we found out the number, we multiplied it by this lowest scale of the calipers, or we can call it NST, which is 0.01 centimeter. So we have 2 times 0.01, which is 0.02 centimeter. Next, we add it by the early value, which is 4.1 centimeter. Then we add it by the early value, we have 4.12 centimeter. There we have the value of the inner diameter of the beaker glass. Next, we must measure the depth of the beaker glass by this small part of the calipers that looks like the tail of it. This one right here, right? Then we just have to pull the calipers here until it's stuck at the bottom of the beaker glass. Then just like before, we lock it with the bolt so you all can freely measure the value of the object again. Next, the way we measure the object is the same as before. We look on the lowest scale, which is 5, and the highest scale, which is 6. And as we can see, the zero number of the vernier or nonius scale is started on the 5.4 cm. Right here, 5.4. Right. Next, we must find out where the nonius scale line, which parallel to the main scale line again. As we can see here, the most parallel line between the main and the nonius scale is on the number 8, right? Okay, next we multiplied it by 0.01 cm. Then we have 0.08 cm. Next, we add it by the early value, which is 5.4 cm. Then we have the depth value of the beaker glass is 5.48 cm. Right? Okay. Right. Okay, the last one we have to measure is the diameter or the outside diameter. Now let's just use the cylinder for this one. Okay, and just like before, we pull the calipers until the outer surface latches onto it. Here, right here, like this. Okay, and then we locked it with the bolt again, and same as before, we look at the lowest main scale, which is 3, and the highest is 4. And then we look at the zero of the vernier or nonius scale, which is started on the number 2. Yep, so we'll have to write down by 3.2 cm for the main scale. We look again on the nonius scale to find out the parallel line between the main and the nonius scale again. As we can see here, the most parallel one is on the number 6, right? Yep, that's right, 6. Next, we multiplied it by 0.01 cm. Then we have 0.06 cm. So after that, we added by the early value, which is 3.2 cm. So we have 3.26 cm for the outside diameter, right? 3.26. Yep. Thereby, that's how we measure object using calipers. Okay, right now I'm going to give you another example to measure the calipers. And as we can see here, the main scale is between 3 and 4, right? And the zero of the vernier or nonius scale is started from number 1. So we have 3.1 cm for the main scale. Okay, wait. So the main scale is 3.1 cm. meter. There. Next, we look at the nonius scale below this main scale and find out the parallel line between the main and the nonius scale again. And as we can see here, the most parallel one is on the number 7, right here, this line. So we write down the 7th line, 7. After that we multiplied it by the low scale or 9st, which is 0.01 centimeter, right? And then we have 0.07 centimeter. So you'll have to write down the nonius scale by 0.07 centimeter. After that, we add up all the values. Then we have 3.17 centimeter. There, the value of these calipers. Next, we write down the report by x bar equal x plus minus delta x. Now this delta x is the uncertainty value of the calipers. The uncertainty value of the calipers is a half of the honesty value. We know that the honesty value of the calipers is 0.01 centimeter. So we divide it by 2, then we have 0.005 centimeter. Thereby, we have to write down the report like this: 3.17 with plus minus 0.005, right? And don't forget to write down the unit, which is centimeter, on the outside. Okay, next thing we're going to do is to measure mass using a house balance or triple beam balance. Okay, next we're going to use a house balance or the triple beam balance. As we can see here, there are different parts of the triple beam balance. The first part here is a pan that used for putting load. The second part here is a thumb screw that used as a calibration screw, so that the equilibrium point in here is at 0. Next, there's a balance arm here, or we can call it beams too. Then the one we put left and right here is called sliders or riders. Next, the unit that we used in this triple beam balance is grams. And to find out what is the lowest scale of it is pretty easy. You'll just have to look at these numbers, okay, here. Now from 0 to 1, Tell me, how many lines that represent a number? There are 10 lines, right? So, to find out what is the lowest scale is you just have to divide 1 by 10, which is 0.1 grams. That is the lowest scale of it. And to find out what is the uncertainty value, you'll just have to divide the uncertainty by 2, which is a half times 0.1 equal 0.05 grams. Okay, next I'm going to show you how to weigh an object. There's a cube here, now we're putting it in here. As we can see here, the equilibrium point is not on 0, right? That means the load is heavier than the balance. Now all you have to do right now is to slide the riders to right and see if anything changes. The 1 gram beam here, as we can see, doesn't change anything on the weight, right? Now let's go to the 10 gram beam. Unfortunately, there's nothing happens on the weight too. Now let's try the 100 gram beam. Here we try on 100 first. There's nothing happens. Let's try 200. And still there's nothing happens. Let's try 300. Still nothing happens. Let's try 400. There we can see there's a change in the weight. Now take a look. If we put the 10 gram beam on 40, the balance is heavier than the object, right? Now after we reduce the weight on 30, there we can see the equilibrium point is a little bit on 0. But still, it's not so precise, right? Now let's try to put the 10 gram beam on 20 and put the 1 gram beam until the equilibrium point is precisely on 0. Now there we go. That's the value. So the value is on 400 on 100 gram beam, 20 on 10 gram beam, and on the 1 gram beam we can see here is on 9.3, right? Thereby the value of the cube is 429.3 grams. That's the value of the mass. We're going to make the data processing. Until this time, we have done measuring from calipers to triple beam balance, right? Now you all just have to write down the value of them in this table. For the calipers, we have measured the inner diameter and the depth of the beaker glass and the outside diameter of the cylinder. And for the triple beam balance, we have weighted a mass of a cube. So we'll just have to write down the report by x plus minus delta x. And the x is for the value of what we found from the practicum before. Plus minus delta x. The delta x is for the uncertainty value from what tools we used before. And lastly, don't forget to write down the units of an object. For the calipers are centimeter, and for the triple beam balance are grams. Okay, that's all for today's practicum. Thank you for paying attention, and I apologize if there's an error before. Have a nice day. Wassalamualaikum warahmatullahi wabarakatuh.